Now, the other things that I sort of ending with a couple of extra slides, sort of as a bit of a note of caution, thinking about, well, how do we assess the model reliability? And this is sort of brought to light by a sort of paper by Omar Brel-Pratt in 2019. And the sort of question here is that we really need to pay some attention to, can the model actually reliably, in a true statistical sense of reliability, I've included the equation here, simulate the event probabilities before we then go on to use the attribution. And this is really important because it can change the probability ratios that we get out, or the fraction of attributable risk that we may then apply to the impacts, to then say, well, this is the cost of this event. And if the model's not very reliable, then perhaps we shouldn't be believing these results. And clearly, you know, we're not going to get the perfect model everywhere. That's just sad reality. You know, we need to do extra bits of sort of model development in order to help sort of boost the reliability. But that doesn't mean to say that we shouldn't attempt to answer the questions and provide information that we do know. So we've got to work out how we can work with this data in order to try and perhaps calibrate it to make it more reliable. And in Omar's paper, he sort of suggests a particular approach that you can use to do this, sort of using ideas from numerical weather prediction, on how to sort of calibrate the ensemble so that you can get a sort of better reliability. And so this is really a good example of where you're using information perhaps or techniques that have been developed in different sort of slightly different domains, to apply them to good advantage to answer the question that you're trying to answer. The other sort of point I wanted to make was on bias correction of the model. You know, quite often, you know, we look at a model and you know, we don't have something that perfectly lines up with the observations. So in for example, as in the bottom left of this plot, a quantile map, you know, we don't necessarily always get everything lined up nicely on the one-to-one line where we've perfectly replicated what the observed sort of statistics of the observations. So we might have things offset, or we might have things sort of going off at an angle, a bit like the red line in this figure. And we need to apply some kind of bias correction in order to improve that. Now, there's obviously a number of ways, ranging from simple to complex, and I'd certainly advocate starting with the simplest approaches first, because there's no way no need necessarily to start applying a very, very sophisticated technique unless we have to do so. But I wanted to highlight perhaps this one particular technique that came out relatively recently in a paper by Sebastian Sippel. And this is where we're trying to actually apply the bias correction in a sort of physically consistent way. So the idea is that you find your variable that you're looking at, and this is you know, likely to be, you know, in your event definition of how you've defined your event, and you can see that is actually sort of biased in the model ensemble. So you can estimate your observational probability distribution, sort of from a fit to the observations, and you apply the same kind of fit, I guess, to the model distributions to estimate the model probability distribution in exactly the same way. And then you can work out a transfer function as to how you go between sort of the model fit functions to the observed fit functions. And you then have a translation from observational quantiles to model quantiles. So you're mapping between the two things. So then you can resample the ensemble based upon what the observed probability of something occurring has happened, and just retaining the corresponding ensemble member as is given by this transfer function. And so you're retaining that sort of physical consistency between different ensemble members that you're using. So this is particularly important if you're considering an extreme event type that's defined by more than one variable. So if you've got a multivariate problem, then you're really not wanting to sort of bias correct and mess with the differences between the different. You want to maintain physical sort of consistency within the ensemble between the different variables, and this is a way in which we can try and do that. And just to say that, you know, bias correction really does come into its own if we're then going on to look at impacts, because you know, quite often if we're trying to study the impacts of a particular extreme event, then it will be defined very precisely, or an impact model will be tuned to take in sort of more realistic or the observed values, and this might not be something that we can provide directly from the model without applying some form of bias correction. So just to summarize, we'd really sort of, I think, you know, in this workshop, you know, as I've already said, we'll be sort of taking the risk-based approach to attribution, but you know, really there's something to be gained by using a combination of these different types of method, using as many different observations and models that we can in order to define the event, and also perhaps think of different ways that we can define the event. Are we defining it by the impacts? Are we defining it by the meteorology that happened, or are we defining it by the circulation? And sort of understanding what that has on the framings and the particular questions that we're addressing. You know, we can use these in combination to sort of fill in different parts of the jigsaw to help give us this fuller picture of what's going on. So I think I'd just like to finish by saying that in general there are some key issues to remember, whichever type of approach that we're using to extreme event attribution. And this is framing the attribution question is key. We really need to think about what is the question that we're asking, why are we asking this question, what is what are we hoping to get out of it, and that will really help us sort of pin down particularly you know, which of these techniques may be the best ones to use, or you know, what sort of question it is that we're really trying to answer. It's, as I'm sure we've already sort of heard lots about, it's really important to define the event in very sort of in a general terms, as a class of event, as a cluster of these types of events occurring. And as I'm sure you have already been told, this is really one of the critical elements of any attribution study. It's also the thing that we end up spending quite a lot of time doing, and you may well need to explore a number of different types of definition before you actually sort of settle on what's the right definition to use as for your particular study that you're performing. And also, whichever approach we take, we really need to assess what biases there are in the model and how reliable the model is. And this is especially important when we're relating things to the impacts of the extreme event, rather than just this event happened, how did humans influence this particular event? So thank you for your attention, and I hope you enjoy the rest of your day.